Billions of years ago, deep in the Earth's past, in the ancient seas and deep under the waves, particulates slowly filter down, sinking into the deepest parts of the oceans where light doesn't penetrate. These particles settle out on the bottom of the sea and over the years slowly build up, layer after layer, telling a story about our ancient Earth. The history of our Earth is narrated by the rock record. Every stone, pebble, and grain has a tale to tell and a memoir to pen. Without them, we would be blind to our past and ignorant to the wonderful oddities found in deep time, such as banded iron formations, aka BIFs for short. They weave intricate tales of a bygone era and one in which geologists are still in fierce debate about. Banded iron formations are sedimentary rocks which were chemically precipitated in the early oceans, mainly during the Precambrian. They contain around 15% iron or greater. They also consist of alternating iron-rich bands of hematite and or magnetite and silica-rich bands of chert. BIFs can contain some iron carbonates and silicates in its structure, in addition to the more common iron oxides, of course. BIFs tend to be extremely hard, tough, and dense, making them very resistant to erosion. The features of BIFs suggest that they were formed in a depositional environment characterized by low energy, so they formed in deep oceans where they weren't disturbed much by wave action and only had to contend with small currents or none whatsoever. Banded iron formations occur all around the world except in Antarctica. They probably do exist on the icy continent, but you can't be 100% sure since they're covered by ice sheets kilometers thick. They're found mainly on cratons. Cratons are the ancient, stable cores of continents, composed of strong, buoyant crystalline rock that has resisted their fate in the rock cycle for billions of years. These cratons can be found all over the Earth and in all 6 inhabited continents today, and are a relic of the Earth's past and help preserve rocks such as BIFs, because unlike other rocks today, BIFs are not actively being made on the Earth's surface any longer. Significant deposits of economically valuable BIFs can be found in Michigan, USA, near Lake Superior, and in the land down under, in Western Australia. These deposits are billions of years old and were formed before the occurrence of complex macroscopic multicellular life. The formation of BIFs are restricted to a relatively small section of geologic time, since they require specific conditions no longer found on Earth. Most BIFs were deposited during the Archean, which was an eon of geologic time spanning from 4 billion to 2.5 billion years ago. And there were also deposits during the Paleoproterozoic, about 1.85 billion years ago. There were also smaller deposits formed during Snowball Earth, a period of intense cold which saw glaciers extend as far as the equator. Interestingly, deposits of BIFs were found in western China, with BIFs dating to the early Cambrian. This was certainly quite an oddity, since oceans were thought to be quite rich in dissolved oxygen, though this deposit may represent a local event of anoxic water which allowed BIFs to form. Banded iron formations were thought to have formed in anoxic ocean conditions, with waters rich in dissolved ferrous iron. In the early model proposed by Preston Card in his 1968 paper, he said that BIFs were a consequence of the activities of cyanobacteria in anoxic iron-rich waters. Since cyanobacteria use photosynthesis to generate energy and survive, they also produce oxygen as a waste product, and back in the Archean, oxygen was deadly to organisms, unlike today. The vast majority of life forms of the early Earth lived without oxygen in anaerobic conditions, so when cyanobacteria started to pump out large amounts of oxygen, this caused many organisms, including, ironically, cyanobacteria themselves, to die off. This increase in oxygen levels in the ocean led to oxygen reacting readily with ferrous iron, and this reaction produced iron oxides, which were insoluble in water, thus causing it to precipitate out the water column and sink to the seafloor where it accumulated. Since the increase in oxygen levels led to periodic die-offs of cyanobacteria, this meant that less oxygen was being produced, so less oxygen was reacting with soluble ferrous iron and producing insoluble ferric iron. In the absence of ferric iron, silica-rich chert also filtered down to the seafloor, forming the partner in the alternating series of rock we witness today. This cyclical pattern is said to have repeated again and again over millions of years. However, when oxygen became firmly established in our atmosphere and ocean chemistry, these periodic events ceased to happen as oxygen reacted with all the ferrous iron and thus depleted it from the ocean. This is how banded iron formations are said to have originated, and this explanation has been repeated in classrooms for decades, taught to new generations of scientists. However, this may no longer be the case anymore. Looking closer, at the geological evidence, this seemingly neat explanation of the formation of BIFs starts to crumble. This process was thought to have occurred after the Great Oxygenation Event, but some deposits of BIFs have been dated to before the Great Oxygenation Event. There's also the fact that since BIFs are really old rocks, with the youngest ones being 500 million years old, they've been altered since their initial deposition, with many undergoing chemical alterations and metamorphosis. Also, the oxidation of ferrous iron to ferric iron doesn't necessarily require oxygen to be the one that accepts the electrons. Electron loss can occur without oxygen, with many bacteria and archaea being able to employ iron as an electron donor and thus oxidizing the iron. An alternate explanation for the formation of banded iron formations is that they were produced via photoferrotrophy. Photoferrotrophy, simply put, is a photosynthetic process where certain bacteria use sunlight to oxidize iron 2+ into iron 3+, and through this process gain energy required for metabolic processes. The thinking goes is that iron supplied through hydrothermal vents on the seafloor were oxidized to produce iron 3+. This process also produced byproducts like ferric hydroxide, greenolite, and siderite. Some photoferrotrophic bacteria create magnetite in their cells, and magnetite is one of the main iron minerals found in BIFs. In the Proterozoic, the oceans would have been rich in sulfides, so sulfide-driven forms of photosynthesis dominated instead, producing iron sulfides. This hypothesis, however, isn't without its fair share of criticism. Critics point to a lack of organic compound found in BIFs, though this lack of organic compound could be explained by other microbes decomposing the organic matter, but perhaps there's a simpler explanation, and that's abiotic processes. Some research indicates that greenolite is actually the original iron mineral found in BIFs, and that other iron minerals are the result of later alterations to the rock, like for example magnetite being produced via metamorphosis. The composition of greenolite in BIFs suggests an abiotic origin dependent on ocean pH, since the majority of the iron in greenolite is iron 2+ as opposed to iron 3+. However, it is formed. Banded iron formations are incredibly important to us humans. Banded iron formations can tell us so much about the Earth and its past environments. Researching them gives us a window into the deep past and helps us reconstruct ocean conditions billions of years ago and interpret the conditions of life on early Earth. And of course, we use banded iron formations as important sources of iron ore. These are some of the most abundant deposits of high and low-grade iron ore, which are mined all over the world. Major ore-producing countries which exploit BIFs for their economic value include Australia, Brazil, China, India, Russia, and South Africa. So BIFs provide billions of dollars in revenue for these countries and employ thousands of people. The story of banded iron formations is long and varied, and such a fascinating tale. Learning about its origin, structure, and its occurrence was quite a joy, and I hope you lot all enjoyed it too.